Okay, thank you everybody. We're going to talk about a little about the productionization of models, a little about the monitoring of them. Everything we're going to talk about here, just to set the right perspective, is all unreleased stuff. So this is all kind of in progress stuff. It's sort of very a real-time snapshot of where we are with these topics. In particular, we are going to show you some monitoring work that Olivier has been working on, and a deployment product, a collaboration. Go ahead and go forward one slide. A collaboration and maybe back one, sorry.
Big backwards then.
Yeah. Collaboration and an end-to-end story. So the end-to-end story of the platform is basically starting from data ingestion, being able to prepare the data, doing modeling, and then of course managing it. And over a period of many years, we've heard from customers that they want more options for how to manage things and more options for how to tell whether the assumptions that they made during the training process are still good and whether they need to retrain or not. And that's where some of the monitoring things come in. And so this is just a quick overview slide kind of showing you the whole stack. Go ahead. So today in driverless AI, in particular, there are two ways of deploying REST servers. They're very pretty basic. One is just a local REST server in the driverless AI instance itself, and then the second way is as an AWS Lambda. And there are other ways, but these are the ones that are actually built into the product. And for those of you that have played with it, you've probably seen these options. There's just a web page in the product that makes these available pretty easily as a push button. And what we want to do is extend that from just a standalone deployment to a more, what I'll call centralized deployment. So go ahead and move forward. And so this is a picture of what we're working on, where you'd have multiple driverless AI instances where today they would be kind of each individually their own thing. Here, what we're going to do in the future is provide a model ops project or product where the different driverless AIs can connect to each other or collaborate, have a centralized repository for model management, for storage of them, for deployment, and for monitoring. And then pushing those models into REST endpoints in a Kubernetes environment, whether it be on-prem or in the cloud, and to make those things be just automatically scalable and easy to reach. So this is something we're working on. It's not available today, but we do have a snapshot that we can show you, and that's what we're going to show.
Do you want to go on this one?
Yeah, go ahead and pull it up. So here, let me go ahead and just clear away these warnings. I'm going to start by showing, I just trained a model in driverless AI before we got here. Here I trained an experiment, and there's a new capability that comes with this model management stack, which is the ability to export a model. And so here I'm going to export this model into the model management software. And basically, I've got a project in the model management software, which is also tied into the monitoring, that allows me to export it. And then the other UI that Olivier showed you before, I'm going to just flip to it, and now we can see it in the actual model management UI. So this is a brand new piece of software. Nobody here would have seen it before. It's basically allowing us to organize models in projects and to use this as a centralized hub for collaboration between data scientists from a training perspective, and also to collaborate from the data scientist to the operations person for deployment. So these endpoints that you see here, a bunch of them were created before, and you can see that there are, for example, different tags that I can apply to models. In this particular case, we've enabled this environment to support 3 different environments, a development environment, a staging environment, and a production environment. And the model that I just exported, we can see it's showing up here as number 6. So I deployed number 4 and number 5 before. One is the current production champion model, and then the challenger model. And number 6 is the one I just made, and here we could easily just go ahead and click one of these tags to deploy it. So trying to be very, very easy, trying to get everybody kind of collaborating in a centralized way. There are other things that we have in here. In particular, if I go back to the projects view, and this is sort of trending to the population stability index stuff. If I go and click on the model itself, one of the things we can download here is the auto report. So I don't know if you guys had a chance to see the session on the auto report, the auto doc, but basically think of that as the compliance documentation or the governance documentation that comes out of driverless AI automatically. And interestingly enough, Olivier, help me flip to one. So here you can see this is a live auto report that we generated earlier. And interestingly enough, one of our big banking customers said, hey, the statistic that I'm interested in to know if the predictions have drifted or not from train to test is population stability index. And as we were looking for different statistics to put into our own monitoring product, we were kind of surveying different options, and the one that Olivier, the Kaggle Grandmaster that's working with us on this project, the one he came up independently with was actually population stability index. So I kind of liked that as a reaffirmation of one of our trusted banking customers said, I like that. Olivier said he likes that. So it's a good place to start. And the documentation is one view, but it's also nice to see, okay, well, what might it look like if we have it live in a product in an ongoing way where we can do this monitoring and be able to ask the question, not just as a document where you're manually doing it, but as a piece of software that's running. Is it good? Are the assumptions that I made in training still valid? Here, let me flip back to the software. I'll show one more thing, which is kind of neat, before I turn it over to Olivier. Here, if I go to the monitoring page, so this is a monitoring page inside the model management software itself. This is basically what I would call a very, very real-time view. It's not doing anything too complicated. Here, it's actually not detecting any drift at all because the drift checks are very, very basic. And Olivier is going to talk about a more sophisticated one in a separate piece of software. Why don't we hand it over to you?
In fact, this is monitoring the what are inside the scoring samples directly, and there is no sort of saying this is drifting or this is changing over time.
It's this one. This view is really basic. It's just the actual predictions themselves. This is a champion and challenger overlaid on top of each other. Here it's predicting is this credit card payer going to default next month? Yes or no? And then of course a scoring millisecond latency view, but very, very basic stuff. And it's
exactly. As a data science company, we don't see monitoring just like CPU values or CPU usage, GPU usage, and memory stuff, and checking the temperature of the hard disk. What we really want to go for is something that tells you is your model at risk, meaning the predictions the model will do, are they really accurate now? Is it still on page? And so what we came up with is something very I have here something directly on my laptop. It's really work in progress. So this is the offline version of the monitoring. And just let me go through an example. So CC train would be the training data that would be used for for training the model inside of driverless. And this test here would be something like 6 months later. And what we want to do is, every so often, we want to check if the data has changed significantly, and maybe send alerts to the people and to the customers so that they can decide if they want to retrain the model or not. So let me start the evaluation. And so we come up directly with a drift score for each feature. And here we see that the feature sex, which is basically gender, has drifted really significantly. And we have pay amount. It's a scoring for banking and credit scoring. So the pay amount has changed as well significantly. So when you see that, you want to check directly the features and their distribution. And what you can see is that effectively for feature sex, things have changed dramatically. The value 1, which is female, I think, has no occurrences or very few occurrences now, when in fact the reference would tell you that 42% of the samples were female before, and here this has changed the same. And you see as well the drift score, which is quite a big one. 0.7 is significant. The same for pay amount. You can see that there are big differences in low amounts and as well in big amounts. So the question here is really to alert the customer and say, have you changed your data? Is it a new population you're scoring? Or maybe there's a problem in your scoring pipeline. You did an upgrade and it doesn't went well, and maybe the samples are not exactly the one you think they are. And we have a last tab with alerts, just saying scores. So let me go back maybe to the presentation. So really, what is data drift? As a data scientist, I would tell you it's a difference in the distribution of a feature. And it can be due to different types of events. Yeah, so as I said, you can be scoring a new population. So maybe you have a credit scoring for the US, and then you want to score people in, I don't know, in China, and this is quite different. So that would be a data drift. And as I said, it can be as well just the pipeline failing due to upgrades. So, and you need to have alerts, real-time alerts for that, and so that you can take action. So there are different data drift. So you see on the left there is you're using a training data, you're modeling it, you're fitting models, on the training data, and then you get training predictions. And then at some point, like Tom said, this model you want it in production. And so you have a scoring pipeline now, and you're sending scoring data to this pipeline, and you have scored predictions as well. So there is a first data drift that would happen on the feature, really on beating the training data and the scoring samples. You would have as well a scoring drift, which is in fact a difference in the predictions you're doing, meaning maybe the scored predictions are not exactly the same as the training predictions you saw during while driverless was fitting the models. And there is a third one, which is in fact the model drift itself. So you need to collect the ground truth of the scoring samples and then check if the overall score of your predictions have changed significantly, and maybe that your models need retraining. So for drift detections and techniques, you have a data science way, which is basically the Kolmogorov-Smirnov test, which is a null hypothesis test. It will give you a p-value saying if your data has the same distribution or not. The bad thing about Kolmogorov-Smirnov is that it doesn't work for all sorts of features. Usually it would work for numerical features. In some cases, categorical would do as well, but that's a problem. And there is the machine learning way we love on Kaggle, which is basically you use your training samples and the test samples or the scoring samples. You concatenate them, and you create a whole new problem where, in fact, you're trying to separate the test samples and the training samples. And if you manage to do that, then that means your data has changed significantly. And so the predictions the model will be doing may not really work well in production. So that would be just really concatenate, train and test, and running a careful on that new data set, and check the AUC score as a for the classification. And an AUC above 0.6 is a warning, and above 0.7, it's usually a significant difference. And actually, we do that in driverless. If you train a model with a training set and you provide a test data set, driverless would tell you if there are differences or not. And usually this comes up as a notification. And so here you can see that driverless tells you that, yeah, gender changed significantly, an AUC of 0.67. And pair-mount 3 as well did change significantly. And it's really amazing because that's exactly what PSI tells you as well, that sex and pair-mount did change really significantly. So the drawbacks of the standard techniques is that you would be using the whole training samples, and that this can be big. And when you do monitoring, you want the data, or you want the monitoring system to be really close to the endpoint. And maybe at the endpoint, you don't have full capacity or a lot of computation power. So using the full training set can be a problem. And as I said, Kolmogorov-Smirnov doesn't work on all sort of distribution. So, sorry. So what we came up with is population stability index, and it works in fact on the distribution of the data directly. So you don't need the full data. The thing is really to create a sort of an image of your data with the distribution themselves, and then check if the test data set or the scoring samples have the same distribution. So here is the computation themselves. Just usually what you would do is really create 10 bins on your data, and for each bin you would compute the frequency, and that's on the training data. You create the bins, you use these bins to calculate the frequencies on your scoring samples, and then you compute the PSI, which is in fact the difference between the frequencies between the actuals and the scoring samples, and you multiply that by your logarithm. And in fact, the logarithm has a few issues. The main issue is PSI is not capped, meaning it can go up to infinity, but it's always positive. So that's the way you would compute PSI. I guess you'll get the slide, so I go over that. And so the pitfalls of PSI is really due to logarithm, meaning that if you have a missing samples in a bin, the score would go up like crazy. And also it's very sensitive to the number of bins. So as I said, usually you would use 10 bins, but what do you do for categorical features? If you have a high cardinality categorical feature, meaning above, I don't know, 1,000, then the frequency for each bin is very small, and chances are in the scoring sample, one bin may be missing. And so the drift score would go up like mad, and in fact, it's maybe not a problem. So what we came up with is a special treatment where we bin categorical features based on their occurrences, on the value occurrences. So that's a special mechanism we put in place. So when I talk about pitfalls, what we're doing as well in the application, on the drift evaluation, we compute confidence levels. So we know exactly in the training data what the occurrences of all possible values. And we can sort of say, in a scoring sample, maybe you can go down to this value here or go up here, and if you really above that, that may be an issue. And in fact, the drift here tells you that there's no issue, and it's probably just because it's just 2 bins. And at the same time, that's a different data set, that's an airline data set, where you get missing values for some carriers that do not appear in scoring samples. And the drift is really big, it's at 2, and maybe it was not that big a problem that these carriers were not in the scoring samples. So what we do in the evaluation, in the drift evaluation process, is really a 2-step process. When during training of the model, we take a picture of your training samples. We do automatic type recognition. We choose the binning strategy. We compute frequencies and confidence levels as well. And then at scoring time, what we do is we collect the data, and so let's say every week we would check, we would apply all these bins on the scoring samples and check the PSI periodically, and then send alerts to customers. So I think that's it for us. If you have any questions, we would be glad to answer.
Yeah, we'd be happy to take questions, and I'd also like to say thanks to the combined team in Prague, Mountain View, and France for this work. This is a snapshot of something that's in progress. We will hope to say more about this at future H2O Worlds as well, as we make progress in this area. Any questions or?
Okay.
No questions? Okay. Oh, there is a question.
Over there.
How do you determine which sensitivity is appropriate for the model? Like when you're binning in 10 bins or multiple bins, what's the criteria to adjust it?
You mean when do we decide that drift is big enough to retrain? So for PSI, the common the common thing is to say above 0.1 there is sufficient drift to really sort of wondering if that's a problem or not. And then I would say you would look at model drift to see if really you need to retrain the model itself. I would say that above 1, you really need to do something about either your data, because either it's changed really a lot and maybe there's a problem somewhere, or you definitely need to retrain your model. So I would say 0.1 is an alert, 0.5 becomes really a problem. And then at 1, there's no question.
Okay, I think we're out of time, so thank you very much.
Thank you very much.